you'll see modules under Loudspeaker Directivity. There's an undergraduate directivity assignment, and there you can download the CAD file for what you're gonna. So I think pretty sure it's a patron theater. And then there's another one here called Polar Plots. So a zip file. It just has some polar plots in it. I'm going to take you through basically what you're going to do for this assignment, but I'm going to do it on a different space. Okay, so I'm going to do it for DeMille. So what we're going to do is I'm going to show you, before we can go through a tool like ArrayCalc or Ease or something like that, I want you to understand, like, what is that app actually doing? What is the math it's doing? What is it looking at, and how is it getting that information? So that's what this assignment is about. I'm not giving you this because I think this is how you're actually going to do it in real life, but I want you to understand how those tools do the thing that they do. Okay, it's not hard math; it's just a lot of math, and you just got to keep track of it. And the good thing is, computers are really good at doing lots of simple math over and over again and keeping track of the results, which is basically what this is. So the task here is basically to figure out kind of what kind of loudspeaker would work best for DeMille Theater. Okay, now what I'm going to do is I'm just going to use the KF300 loudspeaker that is in there. Okay, we actually have an array of 2 of them for reasons that we might get into if we have time in the class, but if not, we won't. But for now, we're just going to do one. And what I've done is I've gone in. You want to sort of start by looking at your section view, and you want to create some seating locations. You want to, at the very least, you want to have front row and back row at head height. And head height, I'll show you how I've done the head height. So you measure up from the ground, basically, looks like I did 3 feet. Okay, that's just approximately kind of where most ears kind of land, give or take. It doesn't have to be precise. And so you put a little point there, and you want to do at least front row, back row, maybe a middle row. I'm going to actually do 4 locations here. So A, B, C, and D is where I'm labeling them. And I'm measuring it at head height based on from the floor. So like here's the floor of the front row seat, right? And I go from the bottom of that all the way up 3 feet. This D spot here is 3 feet up from, where the seat would sit there in that little edge, okay? And then what I did is I laid some construction lines from there up to the ground plan and duplicated those 4 seats there. And then what you got to do is you got to figure out the horizontal seats. Now what I did here, now the DeMille is interesting because it's got curved rows. Mm-hmm. But what I did is I went and said, okay, if I just like follow this line that represents that first row, if I just follow it down, I picked a spot here for seat E, which is like halfway down that row, halfway from middle to the edge. Okay, and I then did an E, and I did an F, which is that's on that same axis, on that same row from B, and then I did a G on that same axis for the same row of C, and the D row doesn't go that far, so I don't need to worry about that. And then what I did is I kept going on the first row and the second row that I'm using, and I went all the way to the edge where I think there will be any seats. Okay, and I said, all right, that'll be row H, and then that'll be row I.
Did you also have to do that for the other side, or technically no, because it's mirrored ideally, but not really?
Yeah, so generally speaking, most loudspeakers disperse symmetrically. Mm-hmm. So if you're trying to save yourself some time, you can kind of do one side and the other side will presumably would be the same if the theater is symmetrical and the loudspeaker is symmetrical.
And in the case of DeMille, you would want to pick the side that actually has the seats versus no seats, correct? To see like that, to make sure it's in line. Because like in the sense, if you look at DeMille, there's a side that has more seats than a nose. So if you were doing to make sure it's mirrored, you would want to make sure you're at least hitting.
Yeah, I mean, I'm sort of imagining, you know, the worst case scenario, right? I mean, they're not going to sit anybody past this spot.
Yeah.
Right?
Yeah.
So I'm not really paying a whole lot of attention to where there actually are seats. I'm just sort of looking at where is the row, where's the farthest place there would be any ears likely.
Gotcha.
And then I picked some, not entirely arbitrarily, a spot for the loudspeaker, okay? So this is where it's going to go, and that's where it is hung right now. It's possible to hang something there. So you're kind of thinking a place where it's possible to hang, there's something to attach to, and you're also, remember, kind of looking for that spot where the front row is about half as far away as the back row is. So you're looking for that spot that creates that little triangle where that distance is hopefully half as far as that distance. Or close, it doesn't have to be perfectly half.
For the horizontal axis, how is it that you, in a sense, did you truly just eyeball it? Was there any sort of math to it aside from just making sure that it was halfway? So, like in a sense, you did the halfway, and moving up or down, you just made sure it was in line and
I mean,
the halfway point?
In this case, it was a pretty specific angle. But that's only because I know something about the loudspeaker that I'm using. I did a 45-degree angle because the loudspeaker I'm using claims a 90-degree dispersion.
So that way you can
and that's just because since this is a particularly wide area and everything, I knew I might need to, so I wanted to have that. In your case, I'm having you do Patrons Theater, so I'm going to be anywhere near that wide.
Yeah.
You probably are going to be able to just do center and then edge, and you'll be fine. Okay.
And again, just one side or...
You don't really need to do both sides. In fact, you know, a lot of ease files that you could download, really, they don't really have the full dispersion. If it's symmetrical, it only has like a quarter of that sphere that's the data, and it just interpolates the rest of it, you know.
Interesting.
Yeah.
And then just also to confirm, it looks like the setup that we have for patrons, it looks like it's how Frankie and Johnny was in the sense of...
Yeah, I've drawn the seats and everything for you.
Perfect. Yeah, no, I just wanted to make sure, because I know patrons are able to move around where everything is.
Yeah. Yeah, just use the layout that I have.
Yes.
Okay, so what I want to do is I want to start measuring some things now. So I've gone in and I've made a little Excel sheet here, and I've got a column for each of the seats. And I have 3 rows for distance, because figuring out the horizontal distance is going to involve some Pythagorean theorem math. Okay, so the C distance is going to be ultimately the answer, but we're going to have to get some other angles to figure that out. So we'll get to that in a second. But that's why I have that. And then I have a vertical angle and a horizontal angle, and this is the angle, you know, away from the axis of the loudspeaker, where it's pointed. Okay. And then I have a row for the distance loss, right? So what is the loss over distance that I'm dealing with? And then I have a row for the vertical directivity loss and a row for the horizontal directivity loss. Okay? So I'm just starting there. There's a couple things I'll add here in a minute, but that's where I'm starting. So I want to start populating this stuff. So to figure out the distance for seat A, B, C, and D, I can measure that straight off of the section view. Okay? So if I go to the section view here, I can just measure this straight off. So to seat A is 22.351. And to seat B is 27.3884. To seat C is 36.6442. No, 33.6442. 6442. The seat D is 38.7703. 7703. Yeah. Okay. So fine. But now I got to figure out these other ones. And it gets a little tricky because if I want to do seat E, for example, well, I can measure this distance, but because there's height involved, it's not going to be fully accurate, is it? So we can use the Pythagorean theorem to figure this out. So Pythagorean theorem says for a triangle, for a right triangle, a squared plus b squared equals c squared. A being one side of the triangle, b being the other side of the triangle, and c being the part of the triangle you're trying to find out, which is us. Okay, so if you can get the distance for a side of that triangle and the distance for the b side of that triangle, you can take the square root of a squared plus b squared, and you will have the distance of c. Okay, so to figure this out, I am first going to just measure one side of this. So I will measure one side of this triangle from here on the ground plan. So I'll go from the loudspeaker to seat E, which is 15.4252. So that'll be my A distance. 0.4252. And then for my B distance, I need to get the height part of it. And you'll notice, oops, come on, that I drew these horizontal lines from the seats. And remember, remember that all of the other horizontal seats are based off of these same rows, these ABC rows. So I can get the height off of here if I go for the row. So the C, D. So seat E is going to be on the front row. So I have this line that is drawn from seat A to a place that intersects with a vertical line coming off of the loudspeaker, okay? So it's this distance from the height of the loudspeaker to the point vertically where it intersects with that line representing the front row. That's the other side of that triangle. So I want, that is 17.75. Okay. Okay, so now to figure out C, I have to do that math, okay? So I can use Excel to help me with this. So we can do a square root of that plus that squared. And just to make sure it doesn't get confused, I'm going to add some extra parentheses just to make sure it does everything in the right order. Okay, so you see what I did? I did F2 squared, and that little upside down V is like to the power of, right? So square root of F2 squared plus F3 squared, which are those two values, that's the actual distance to that seat. And just to like check the math here, we know the seat A is 22.3 feet. We would expect seat E to be a little bit farther away, right? Because if seat A is right there where the loudspeaker is, and then you go over here to seat E, there's going to be some extra distance involved there. Okay, so as long as seat E is a little bit farther than seat A, then I think I know I've done it right. If it's like massively different, or if it's shorter, then I did something backwards, right, or something wrong. Okay, so it looks like I did it right.
Your screen will be recorded, right?
It is recording, yes.
Okay. Just want to confirm.
It's trying to record.
Gotcha.
Okay.
Refreshments is being all weird.
I know. Okay, so all right, let's measure the other stuff now. So if we go to seat F, this thing, we can measure this one, and we're going to go from here to seat F, and that is 26.1092. 1092. And then if we do the B distance, see, I've drawn that line to intersect with that vertical, so we can get that side. And I will do here to there, and I got 15.25. Yeah, 15.25. Okay, now I should be able to just kind of copy this formula over, and it should give me the same thing, right? Because it'll just shift those cells, G2 to G3. Okay, so this should be a little farther away than seat B, and it is. So seat B is 27, seat F is 30, so that makes some sense. Okay, you with me so far?
Yes.
Okay. All right, so let's see if we can figure out seat G. So when you use a tool like ArrayCalc, this is what it's doing. It is figuring out, now it's doing a lot more than, 7 or 8 seats. It's going to do thousands of points all along that area. It's going to do this same math thousands of times. Okay, we're not going to do it that many times. 34.7437. 7437. Okay. And then let's go down here and get this one, which will be to there. 11.0417. And then same thing, I'm going to just copy that over. And this should be a little bit farther than seat C, and it is. So that makes sense. Okay, so now I got to get H. H is 18.7827. And then the B value here is going to be the same as CE because it's on the same row, right? So I can just take that and copy that over. I don't have to measure that again.
Would that also be then for F and I?
Um,
Or are they the same? No.
yeah. So I would have the same value for F.
Okay.
Yep, so we can copy that over. So yeah, let me just got to get the distance to I here. Uh, 29.1694. Okay, and then I can copy this over. And that should be my answers, okay? All right, so I have all the distances, yeah? Now the question is, where are we going to aim this loudspeaker? Well, we're professionals, so we're going to aim it at seat D, which is the back row center, okay? So let's start there, and this would be a vertical angle of 0 and a horizontal angle of 0. That's where we're going to point the loudspeakers, at that seat, okay? And I'm going to show you a shortcut for the distance loss from what I showed you last time. Just now that you can see how to figure that out, we're going to do the shortcut. And basically, all we really care about is how much different are the other seats than this seat. So I'm going to put a 0 here for distance loss at seat D, because it doesn't really matter what it is. I will have lost something. All I really care about is how much quieter or louder are the other seats than that seat. Okay, for purposes of directivity. Now you can also do the math to figure out, well, how loud could I make that loudspeaker at that on-axis point? We know how to do that math. And then this little chart will just show you, okay, well, if that ends up being 90 dB SPL, and you know that all these other seats are -6, -5, -4 off from that, then it's easy to figure out. Okay, so we're going to put 0 there too. And therefore we have no loss from going vertical off axis and no loss for going horizontally off axis. So seat D is the reference. Okay, so we can start figuring out distance loss by doing some simple math, because all we really have to do is compare one distance against another distance, and we'll have it. So we want to do a base 10 logarithm of, let's see, seat D divided by seat C, for example. Or no, it would be, we're doing A, so seat A. If we just do this off of those two distances and then multiply that by 20, we will get the dB difference between sound traveling those two distances. Okay? So seat A, which is the front row, should be 4.78 dB louder than seat D, which makes sense because it's closer, it's a shorter distance, right? So it should be louder.
And it was the reference of D over whatever it is you're comparing it to?
Exactly.
Okay.
Exactly. So what I'm going to do is, in my little Excel thing here, I'm going to put little $signs in front of this E4 so that it doesn't migrate that cell when I copy it. When you do that, it'll keep that, but it'll shift everything else. So now, if I copy this over, those should update. Yep. E4, D4. Then I can move this one over here. And copy these over, and these should all populate. F4 against E4, G4 against E4, H4, yep. Okay. Yeah? So they're all positive numbers because they are all closer than seat D, which is where we're aiming. And that's the point, right? Is we're aiming at seat D because that's the farthest away. And so when we go off axis and we lose level from going off axis, we're hoping to gain that level back because we're getting closer. Okay? So this is just one of the ways I check my math. I would expect these to all be positive numbers because I am aiming at the farthest seat away, which means every other seat should be louder. Okay? All right, so now we just have to measure the angles. Okay? So if we go to the section view, we'll start with seat A. So I'm going to measure the angle between seat D and seat A, and that is 41 degrees. So the vertical angle is 41. And then I'll do it again for seat D to seat B, and I got 23. So 23 there. And now we'll do seat D to seat C, which is 8 degrees. Now, I can now just copy these over because these will be the same, right? Because seat F is going to be the same 41 degrees as will seat H. Seat B will be the same for F and I. And seat G will be the same as seat C in terms of the vertical angle. So now I just got to get the horizontal angles. Well, for ABC, the horizontal angle is 0, right? Because those are on center line. So I really only have to figure out horizontal angle for E, F, G, H, I. Okay, so we'll do an angle. We'll do E, so that's that line against that line, and that's 45 degrees.
Just to confirm, it doesn't matter where in the line you're clicking because
Nope.
you're comparing
Doesn't matter.
angle. Okay.
Yep, and so F and G are also going to be 45 degrees. All right, so now I just have to do H, and there we go, and that is 74, so this will be 74, and that'll be 74. So that's why I positioned the seats the way I did. The horizontal ones, I did them all on that same line so that it's the same angle. It just makes the math a little easier. Now, when you're using Array Calc or Ease or Sound Vision or something, like it's doing a whole lot more points, right? Tons more. All the ones in between, every angle, it's giving you as much resolution as it can. Okay, so we've got the information here. I'm going to save this as my Directivity demo. So now I just need to start plugging in the loss that I'm going to incur because of Directivity. Now, I have pulled up the polar plots for this KF300, and in that zip file that I have on Chrome, or on Canvas, has got a bunch of different polar plots. You can use those, or if you want to go and find some of your own online for different loudspeakers, you can. Not all manufacturers are publishing polar plots these days because they're now just publishing them in the digital file formats, the Directivity formats, but you can still find them. But if you don't want to do that research, that's fine. You can just use the ones I gave you. That's totally fine. But you can see this is kind of an older loudspeaker, and the manual that just has basically the spec sheet for this thing is 48 pages long because they have to do all the polar plots. So I'm going to go find the vertical polar plot for 2 kilohertz. Because 2 kilohertz it should be solidly in that area where it's consistently directional, right? And that's what I'm going to have you guys do too, is 2 kilohertz. Now, when other computer programs do this, they're going to check multiple frequencies, okay? But for our purposes, we're only going to do 1 because it'll just take forever if you have to do multiple frequencies. So just stick to 1. And so here is 2,000 hertz vertical, okay? And we want to know what does 41 degrees off axis vertically do to us. Okay, well here's 30, and there's 60, which means 50 and 40. So 40 would be about here, right? So 40 looks like it intersects right about here with the minus 12, but not quite. So I'm going to say minus 11. Okay? So we have lost minus 11 dB vertically, but nothing horizontally at seat A because we haven't gone off axis horizontally. Okay? Okay, now seat B is 23 degrees, so let's find that. So there's 30, which means 10 would be here, 20 would be here. So 23 is somewhere around there. So we're getting close here. I mean, we can't precisely measure these polar plots, right? So a little bit of just like getting close. Okay, it's not quite hit the 6 dB, so let's do minus 5. Okay, now seat C is 8 degrees, which will be, that's 10, so, it's maybe dropped a couple of dB. Not quite 3, but we'll say 2. So minus 2. And then, of course, 0 for seat D. So I can now just copy these over. Okay. For that. And then H and I would get the same 11 and 5 because they've got the same vertical angle, right? Okay, so now let's start looking at the horizontal. So I have to back up here and find the horizontal 2 kilohertz. There it is. Okay, so the first angle I'm looking for here, I don't need to do these, so I just need to do seat E, which its horizontal angle is 45 degrees. So 45 is lining up pretty much right at that 6 dB down point, which is on purpose. So that's -6, which means that's going to be -6, and that's going to be -6. So now we need 74 degrees. Okay, so that's 60, that's 90, so 70 would be about here. So at 74, we've gone just a little bit past the -12. So we could say -13 or maybe even -14. We'll just say -13. So we can do the same thing there. Okay, so we've got all the information now. So now what is the ultimate answer?
Where to put the speaker?
Well, I just want to know what is the total loss difference at each of these seats, right? So total loss. And that's just going to be the sum of those 3 things, right? So I'm going to do sum of those 3 values. And I can copy that across all the way, and I should get it. All right. So that is, this line here, that is showing how much different each of these seats are from seat D in terms of loudness at 2 kilohertz. We have the worst one is seat H, which is 20 dB quieter. Now, it's not actually that bad, because what we're doing is we're actually summing the vertical and horizontal loss, and in truth, if you could, because that's all we have, but in reality, you know, this is emanating spherically, and so it won't be quite that bad, because we're just summing those 2 extremes, and really it's going to be somewhere in between when you find that spot where it actually hits. But that's the information we have, so that's what we have to work with. So it's probably not going to be quite that bad, but this is certainly, I've got a whole lot of seats that are more than 6 dB. And once you get, you were looking for no more than 6 dB difference from the on-axis point. So there we go. I've got it. I've plotted it. Now this is neither right nor wrong. It's just information. I need to figure out what I want to do with this information. Well, the first thing I'm noticing is I do not have as even a dispersion as I would like. Okay, so what do I do about that? Well, I could go find a different loudspeaker that had wider dispersion. That would be one option, because this one is spec'd at 90 degrees horizontal, and that's not quite going to cut it. Because my farthest horizontal angle is 74 degrees on one side, which is a total of 148 degrees, from end to end. So I would need to find a loudspeaker that has that wide a dispersion. Those exist, but not very many of them. But the other thing I could do is I could just use 2 of these, right? I could splay them horizontally. And we learned in the engineering class last semester that if you splay 2 loudspeakers like that and you line up their 6 dB down points perfectly in phase, then you get a perfect reinforcement. Basically, in between the 2 axes of those 2 loudspeakers, when you get them splayed like that, you have effectively on-axis response across that entire area. Okay? So what if I did that? What if I just took this thing and turned it so that the 6 dB down point actually lined up on the center line? Then what would happen? Because then I could see, well, what would be my dispersion all the way to the edge then if this was aimed at the 45? Because then if that's okay, if that gets me what I want, then I know I could have a mirror image of that thing also lined up at negative 45, and they would sum together and be just fine. So
those cabinets built for that?
yeah, they are.
The sides of them line up?
Yeah. Well, there's a sub that you can buy
Yeah.
that goes between them that actually puts them in that perfect angle to array them, and that's what we have in DeMille. Okay. Okay. So let's, now that we have this, let's try this idea. So I'm going to call this sheet single KF 300. And I'm just going to copy this sheet because I don't want to like lose what I've done. So I'm just going to make a copy of it. And we'll call this the double KF 300. So in this case, what I'm going to do is I'm going to aim this thing on this 45. I'm going to effectively aim it at seat G. Okay. So seat G now becomes the 0. Okay, so this is now 0, 0, 0, 0, 0. So now I just have to change all of this. So let's get new angles now for the vertical. So to seat A, I'm now going to compare it against seat C vertically, right? Oops, angle that to that. Okay, that's 33 degrees. Seat B to seat C is 15 degrees. Seat C is going to be 0. And seat D is going to be 8 degrees vertical. Okay, so this now means that I can copy this. So this becomes 33. This becomes 15. That's 0. This becomes 33. And this becomes 15. Right? But now I got to do horizontal angles, because now I'm off. Well, I know that horizontally to these seats, we're now going to be 45 degrees off, because I've rotated it. So this is now going to be, I'm going to call it minus 45, just to remember that it's on the other side. And this will be 0 now for horizontal, because it's aimed at this axis. So now I just need to do seat H and seat I, which are going to be nowhere near as far off as they were before. 29 degrees. Okay. The distances are the same, right? I didn't change how far any of these seats were away from the loudspeaker. Right? So I don't have to remeasure any of that. So now the distance loss is going to stay the same. Except, well, the distance loss probably needs to be recalibrated. The actual distance is the same. But the distance loss, now everything needs to be referenced off of that seat. Right? Seat G. So now I can go in and copy that. looks right. And that. H4 to E4, H4, F4, H4, yep, okay, and we'll do that one. That is H4 to I4, J4, H4 to J4. Yeah, okay, so I redid the distance loss just to account for it, pointing at a slightly different seat. That'll just tell me the difference between compared against that seat now instead of the other one. Okay, so now let's find my vertical loss. So these are all going to change now. So let's start with seat E, because that's where we're on axis to, right? Mm-hmm. So 33 degrees, vertical. Let's go find the vertical again. 33 would be right about here, which is going to be, it looks like it's about halfway between the 6 and the 12, so -9. Okay? Now, seat F is 15 degrees, which is going to be right about here, and that's halfway between the 0 and the 6, so that'll be -3. Seat G is 0. Okay, so now all the ones that are 33 will get the -9. We'll get a -9. All the ones that are 15 will get a -3. And I just need to figure out seat C vertical loss should be 0, right? Because I'm aimed at that row. So that can be a 0. I just need to figure out D, because that's that 8 degrees this way now, right? Mm-hmm. So 10 would be about here, so 8, we're looking, I would say -2 there. So that'll be -2. All right, so there's all my verticals. All right, let's figure out the horizontal loss now. So I've got this -45 I got to deal with. So let's find that. So here's -30. So 45 should be right there. It should be right at 6 dB down. Based on the specs of the Loudspeaker, and the polar plot confirms that. So it is -6. -6, -6. Now seat E is going to be no horizontal loss. Seat F is no horizontal loss. Okay, so let's look at the 29 degrees for H and I. Well, 29 is just right shy of 30, which it's a little bit more than halfway between 6 and 12, so let's call it 4. It's -4, -4. Okay. Now, assuming I'm going to do 2 of these, and I'm going to line them up perfectly on that 6 dB down point, that means these -6s will actually become 0s, right? Yeah. So I'm going to make them 0s, which means here's my new result, which is significantly better. Okay? I am within 6 dB for every seat except seat H. And seat H is this really extreme front row seat. And my guess is that it won't be quite that much because, again, I'm summing that vertical to horizontal, and in real life it'll be like somewhere in between. So it's going to be, you could probably knock a couple of dB off of each of those. And that'll be about right. But but that's the data we have, so the resolution we have. So we'll be like, okay, well, worst case scenario, that front row all the way to the side, that's going to be my worst one. And so either I just assume that it's going to be better, because it probably will be, or I design my way through that and do like a front filter or something to fix that problem. But based on experience, I know that it's not going to be that bad. Okay, and you could verify that when you go into space. You could use SMART to measure these levels to see if it's tracking, if your prediction is tracking with real life. You could go put a mic there at seat H and put a mic there at seat G and compare the SPL difference, and you would be able to see how much it is. Okay, so this will work. I can do 2 of these, and I'm within 6 dB, right, all the way across. So that works. Now, to really prove the point, I would have to go and do this for multiple frequency bands. So I'd have to do this for probably 4 kilohertz, 1 kilohertz, and maybe even 500 hertz. Those would be the frequencies we tend to care the most about. To see how it would work, it just adds up really quick, becomes a lot of information. But this is the basic process. So your mission is to take that CAD file I gave you, and I want you to use those polar plots that I gave you to, I want you to plot at least 2 different loudspeakers onto that seating area. Pick a spot to hang something, someplace where you know you can hang it, point it at that seating area, and then plot it out. Tell me what that looks like. And for 2 different loudspeakers. And then I want you to look at that data and tell me which one is the better choice. Okay, that's all I need you to do. Now, if you want to put some thought into which loudspeaker you choose, if you want to measure that seating area and look at the angles and look at spec sheets and try to figure out which one is likely to get you the best result, you can do that. I don't need you to do that for the purposes of this assignment. The making the judgment part of it, we're going to get pretty deep into that later. All I need you to understand right now is, how does the math work that figures out how a loudspeaker disperses sound over a listening area? Right? What is actually going on there? And to understand that it is a combination of loss over distance and loss from directivity. And understanding how those answers are derived is the point. I don't need you to be making good choices yet. Okay? So literally pick any 2 loudspeakers, plot them, show me how they disperse, and tell me which one is better. Okay? Which one disperses more evenly? Do it at 2 kilohertz. Okay? Questions?
I opened up the CAD file.
Uh-huh.
I was trying to follow along at the same time as you. And just a question that I wanted to ask on the patrons one. There's already 2 points on what looks like A and D on the section view. I was wondering, are we supposed to use those points as reference for A and D?
Those are things like the set designer usually, those are like called the sightline points.
Oh, okay, cool.
Those aren't part of the assignment. You can use those if you want.
Oh, good.
But
when I measured it, I was
Yeah.
like, it's 4 feet, and I couldn't remember because I thought you said 3 feet, but also don't
Yeah.
know if 4 feet is fine to aim at in the sense of like if I want to pretend that those points are my A and D. I don't know if I should.
They did 4 feet.
I think so. That's what it looked like.
Oh yeah, yeah. I usually do 3 feet.
Okay. Just wanted to confirm
but-
that.
It doesn't. I think most of the prediction programs usually do like 1 meter.
Mm.
So they usually do like 3.28 feet. Just because a meter is a nice round number, but
Yeah.
obviously people are different shapes and sizes and heights and everything, so it's not like, it doesn't really matter, give or take 6 inches and you're going to have similar results. Yep, so you can certainly use those if you want, but go in and figure out, plot some spots along the side here. My advice is keep them on the same rows as these. So if you can do a center row if you want. You probably should. So pick a center row, and then go over here to the side and do a side point for each of those 3 rows. Okay? And
So when
that-
you're saying you want us to do a center one, does that mean you only want us to do ABC? Because I was getting ready to do ABCD, so technically splitting it, so it wouldn't be center, but it would be split center. Do you want us to do then ABC so that way we have like a dead center?
Yeah, I'm not expecting you to do an array. I'm not expecting you to do multiple loudspeakers here. So,
Yeah, no, it was just more so when you had it, you had like
Yeah.
the ECG.
so I did 4 just because of the way DeMille works.
Yeah.
Because I knew that the actual back row of DeMille in the center sort of, gives out before you hit that 45 degrees. So that's why I added a 4th row, is because I knew eventually I was going to need to aim at 45, and I wanted to be able to aim at a spot I could measure.
Gotcha.
You don't have that problem for patrons, so you could probably get away with just doing 3.
Okay.
If you want to do 4, that's totally fine. But the main thing, just to make your life a little bit easier, is to make sure that the side seats that you're marking are on the same row as the centerline seats.
Yeah.
Otherwise, you have to do some extra measuring that will slow you down. Other questions? So I just made that look really easy. This is tricky. I would suggest starting soon so that if you get stuck, you can find me and we can look at it before Tuesday, okay? Because I want to come back Tuesday with this done. I just did it in 45 minutes, and that was me going slow because I'm trying to explain it to you. Okay, so if I was just doing it myself, I probably could have done it in half that time. So 20 minutes. My rule of thumb is it usually takes you guys about 10 times longer than it takes me to do something. So if it takes me 20 minutes, it's probably going to take you at least 200 minutes.
I think it'll depend on how soon you upload the YouTube
So
video.
plan on this taking a couple hours.
Okay.
Is my guess. And yes, I will upload the video right now because otherwise I will forget.
Oh, good. I also
So-
have it recorded because I had a feeling that